So this is the M2 International, the second part, M2 International January 14. We've done questions 1 to 4 in the first part. So let's go get going with question 5. It's a moments equation. It's not particularly standard. It's not difficult in terms of the forces. There's not that many forces involved. There's a reaction force and there's a friction force because it says the ground is rough. It also says that it's uniform, so we've got a weight halfway along there, and we've got a tension along the rod here. Okay, and it's given us for part A, it's given us a very good hint, and it's saying take moments about D to get this relationship here. So we better just take moments about D. Good thing about taking moments about D is the R force doesn't have a turning effect because that has a line of action through D, and so does the tension. Okay. So the only forces involved here are the F force and the mg force. Right, now the F, well, remember the moment is force times perpendicular distance, so it's F times 2a. Now, to work out the moment of the mg force, it's probably easier in this particular case to actually look for the perpendicular distance rather than to resolve into components, because it wouldn't be easy to resolve into components that go through D and perpendicular to D. So that distance is not particularly difficult to find because this length here is A, so that distance is A sine theta. So we can say that it's equal to mg times by the perpendicular distance, which is A sine theta. Now A is going to cancel. Okay, so A will cancel. And so then we are left with the thing that we've been asked to prove, which is mg sine theta over 2 as required. Okay, so that's the first part. Second part, part B. It says find the magnitude of the normal reaction force. Now we've got F in terms of mg and sine theta. That's going to be useful. Now it might be tempting, as in most questions, moments questions, we're resolving vertically and horizontally because they're normally simpler equations to get. We normally want 2 or 3 equations at least, and resolving horizontally and vertically are 2 easy ones to get. But in this case, it would be a bit more problematic because it's that straightforward to work that angle out. So it would probably be easier to take another, it's a bit unusual, to take another moments equation about point C. And the advantage of doing that is that C, the force T, will not go will not have any turning effects. It won't be in our equation. Okay, so let's mark on, let's resolve some forces here. The mg, let's mark on the angles first. That theta, we've got this component here will be r sine theta. It will be sine because it's not next to the marked angle there. This point, this one here, well, if I mark the angle on here theta, which it is, 90 minus, because 90 minus theta here, so it's theta there. So this one is F cos theta, because if the arc that you'd mark along the angle comes next to the component you're looking for, then it's cos. Right, now this one here, let's mark on the angle carefully. We've got this angle here is theta, so this component here is F not f, mg sine theta. Right, now let's look for some distances. This tiny little distance here is actually going to be a over 3, because that's 4/3 a minus a, because mg, it's a uniform rod, so that's 1/3 a. So we need that in our moments equation. So let's take our moments equation. So we're taking moments about c. The clockwise ones are the f cos theta. Remember the other, it will have another component here, but that goes through the centre, that goes through the line of axis of C, so it's only the perpendicular component we need to consider. So that's f cos theta times by the perpendicular distance, which is a. Then let's do the mg sine theta, so it's plus mg sine theta times by a over 3. Okay, and then those are going to be equal to the anti-clockwise moments. That's our r sine theta here, which is a perpendicular component, times by a. Now, of course, a will cancel. Okay, and if I now substitute for f and do a little bit of messing around, just a sec. Have I got the distances wrong? It does look like I have got the distances wrong, because of course we're at C, not at the midpoint, which is 4/3 away. So that the f cos theta is 4/3 a. Go back to blue. And the other one is also 4/3 a. And a cancels. Okay. So we can multiply through by 3. So we'll get 4 f cos theta plus mg sine theta is equal to 4r sine theta. Now we can substitute for f, and then we can get an expression for r. So if we substitute for f, we have 4 mg sine theta over 2 times cos theta plus mg sine theta is equal to 4r sine theta. Now, looking at this now, sine theta will cancel. We will end up with this term here, with the 4 will cancel with the 2. So that will be 2 mg cos theta plus mg is equal to 4r. So that gives us r equals to mg over 4, 2 plus cos theta. Now that's the answer. Now I have had students get quite concerned at this point, because they think, well, we've got a lot of unknowns in there. But of course, they consider it would have been nicer if they, or easier if they'd said in terms of mg and theta, but they're expecting us to know that these are no way determinable from the information that they give. So answer needs to involve m, and it needs to involve theta, and g is just a constant that we know. So they expect us to kind of see that. Okay. Then the next question is, find it says, given it's in limited equilibrium when tan theta equals to 4/3, find the coefficient of friction. Well, we've got tan theta equals 4/3. I'm going to do a bit of work with the angles here. Reluctance to use a calculator. We should easily convert using a 4-3-5 triangle, basically, or whatever. Should easily be able to convert that to sine theta and cos theta, because that means that sine theta is 4/5 and cos theta is equal to 3/5. So that might help us to work out f. So that just tells us that f is equal to mg sine theta, which is 4/5/2. So that's equal to 2/5 mg. Okay, and then if you substitute cos theta is 3/5 into there, I get r equals to mg/4, 2 plus 3/5. So I think that comes to, if we work that out, it's 13 mg/20. Spotted as another silly mistake in my factorisation there, which has affected what I'm getting here. That should be a 1, and this should be a 2 here, which means that that's 1 plus 2 times 3/5. So it doesn't make it 13 mg/20, it makes it 11 mg/20. So let's write it, the next bit over here. It's in limiting equilibrium. Which tells it this is f is equal to mu r. So that tells us that mu is equal to f/r, which is equal to 2/5 mg over 11 mg/20. So that answer, when we work with that, that gives us for 8/11. And finally work that out, which is fine, and we can leave that there. So okay, not yeah, a little bit tricky, a little bit unusual. We didn't have to resolve it horizontally or vertically. Anyway, it's done, and we can move on to the next question. Okay, lots of blank pages again. Okay, right, now this is it's 8 marks, so that's kind of saying something about the question. Projectiles with a bit of energy thrown in. Okay, it's given this is our initial velocity here, and it's saying that the ball passes through A when t is equal to 15/49. Right, so I'm going to use energy first of all to work out what E is. It says, so let's work out what E is first. E is equal to half times m, whatever the mass of it is, times by 3 squared plus v squared. Okay, because of the two components. You don't, I mean, obviously we could just say the magnitude of that is, the velocity is that, and then squaring the whole thing, but of course that's just going to undo itself. So That's the kinetic energy. You can just do the individual components. Okay, I'm just going to then rewrite that as 2E over m is equal to 3 is equal to 9 plus v squared. Okay. Now, we are told that E is equal to half the amount here, but the problem is we don't know the velocity there. But we are told that T is equal to 15 over 49. When I say we don't know the velocity, we of course do know the horizontal because that stays constant. What I'm saying is we don't know what this vertical bit is here. So what we can do is apply V is equal to U plus AT vertically from 0 to A. Okay, well we've got, let's call it V at A for this purpose is equal to U, which is equal to V, because we're looking at the vertical component here, minus G times by T, which is 15 over 49. If ever they give answers which are, if ever they give things with 49s and such things, it probably means we want to work G out, because 49 cancels nicely with 9.8, and that makes it a fifth. So I think that makes it equal to V minus 3. So that means the kinetic energy at A is equal to, which is equal to E over 2, because we're told it's equal to E over 2, is equal to half times by m, and this time it's the vertical component, the horizontal component, which is constant, that 3 here, and the vertical component, which is V minus 3 squared. Okay, well that should work out quite nicely because we can just substitute for E. I'm good. Yeah, and the 2 cancels as well. So we can say that E over m is equal to 9 plus V minus 3 squared. So we can see that the kinetic energy here is twice as much as the kinetic energy here. So if we double this, we're going to get this. So we can set up an equation. So we can say that 9 plus V squared is equal to 9 plus V minus 3 squared. And that amount is, of course, times by 2 because it's double the energy. Okay, so that gives us 9 plus V squared is equal to 18 plus 2 times, let's multiply that out now, V squared minus 6V plus 9. Okay, so that gives us 9 plus V squared equals 18 plus 2V squared minus 12V plus 18. Yeah. So if we take the V's over to the one side, we get V squared minus 12V. We've got the 36 take away the 9, which is plus 27 equals 0. So that gives us V minus 3 is a factor and V minus 9 equals to 0. But we're told that V is greater than 3, so we've got V is equal to 9. Okay, not too bad. A little bit, again, they do like making up kind of slightly different questions every time, but if you use the principles, not really a problem. Okay. Now, let's just look at the next part. At another point B on the path, the kinetic energy is also half EJ. The ball passes through B at a time t seconds after the projection. Right, okay, well, that's kind of interesting because they're basically expecting us to realise that this is going to be at the same point here, because the gravitational potential energy will be the same at that point. So the kinetic energy will also be the same at this point, so it's in line. Okay, well, we've got that the velocity at that point must be equal to I'm talking about the velocity here, 6, because it's v minus 3, the vertical component there. So this must be going exactly the same, minus 6 downwards at that same point. This is the point B we're talking about here. So we can therefore apply V is equal to U plus AT again, but with V equal to minus 6, U is equal to the initial velocity, which we now know, which is equal to 9 minus G big T, because they want to call that the value there. Okay, so that gives us G big T is equal to 15. So T is equal to 15 over G. Sometimes that's accepted as the answer, but I do think it's advisable to give the answer to 3 or 2, in this case 2 significant figures will do, because we've got G in the answer at 1.5. Okay, so that is question 6, and I think we're now on to the last question. The blank page again. Okay, right, so we've got a little bit of collisions going here. Right, let's just see what we've got. We've got 3 particles A, B, C, each of mass m. So m is going to cancel. Nice. And we're going to look at it. We've got the particles A and B are projected directly towards each other. So before, it's always good to do a before and after diagram. Before, we've got A is going towards this one with 5u, and B is going in this direction with 4u. Okay, and then afterwards, well, C, of course, isn't involved in this. It's or is it particle A and B are projected directly towards each other with speed 5u and 4u respectively. Particle C is projected directly away from this. All right, okay. So that's actually being given a velocity 3u after that. So this is the diagram for the first collision. Obviously, this is A, B, and C. C is not going to be involved with the first collision, so that's still going to be puddling along there. 3u. And let's call them, I tend to use a numbering system with this rather than, because just in case we run out of symbols. Let's call this one here V1, and this one here V2, the velocities of A and B after the first collision. So conservation of linear momentum equation is involving the for the first collision involves A and B only. So that's 5mu minus, because it's going in the other direction, 4mu equals to mv1 plus mv2, and obviously m cancels, so we end up with an equation. If I reverse that, we get v1 plus v2 with m cancelling is equal to u. Okay, so then let's do our Newton's law of restitution, sometimes called Newton's experimental law. So Newton's law of restitution, now we're only told that it's E. Okay, so we can, the E is equal to speed of separation over speed of approach. Okay, so E, now the speed of separation is the difference between, now V2 is going to be the larger one, so that's V2 minus V1, and the speed of approach, well, these two are going towards each other, approaching towards each other relatively with 9u. So that's given us that V2 minus V1 is equal to 9u. Okay, and what's the question asking for? Oh, it says find the speed of A immediately, so it's just finding the speeds of A and B. So it's quite a nice question, really, quite standard for the last question. We've seen harder stuff earlier on in the paper. So the if I add these two together, then V1 is going to cancel. If I add these two together, V1 is going to cancel because I've got a positive V1 in the first equation and a negative V1 in the second one. So I'm going to be left with 2V2 is equal to, oh, I've forgotten the E from here, is equal to 2V2 is equal to U plus 9UE. Okay, so that gives us V2 is equal to U over 2, 1 plus 9E. Okay, and then we can, what I might do, rather than sub that back in, I might choose to subtract these two, because then that will eliminate the other one. Subtract, because I'll get rid of V2 by that way, and I'll end up with 2V1, because V1 take away negative V1 is 2V1, is equal to U minus 9UE. So V1 is equal to U over 2, 1 minus 9E. So that's it. That's that done. Right, let's tidy this up a bit. Okay, so it says, given that the direction of motion of A is reversed for part B, between A and B, the direction of motion of A is reversed. That must mean that we have the V1 has got to be actually less than 0 for that to be the case. So in other words, I've marked this on going in that direction. If they've now told us it's going in the opposite direction, that must mean that the actual expression that I've calculated here must be negative. So that must mean that 1 minus 9e is negative. So that gives me the fact that e is greater. Oh, let's not rush this. 1 is less than 9e, so e is greater than 1 over 9. Okay, so you might be thinking, oh, that's it, but it's not. It also gives us another piece of information, which says that there is no collision between B and C. So these do not collide. Well, notice that C is going with speed 3u. So if V2 was to go with a speed more than 3u, it would collide. So if there's no further collision, we can't have that to be the case. We need V2 to be less than 3 over u. So that implies that V2 is going to be less than 3u. Okay, well, we've got our expression for 3u, so we can just work with that. So we've got 3u is, let's write it in the right way around. We've got u over 2, 1 plus 9e has got to be less than, which our V2 has got to be less than our 3u. Okay, so the u is going to cancel. Times by 3, we get 1 plus 9e is less than 6. So we get 9e is less than 5. So that gives us e is less than 5 over 9. So we've got an inequality which we can combine into 1. E needs to be greater than 1 over 9 in order for one of them, for particle A to have reversed, and less than 5 over 9 in order that there should be no further collision between the two particles. Okay, so I hope that you enjoyed this past paper. There were some a little bit challenging questions there, but the last question was a bit of light relief in comparison. Okay, cheerio.